Well, good afternoon, everybody. My name is Richard Chuchla, and I'm the director of the Energy and Earth Resources graduate program. My background is my early career was in mining, base and precious metals and coal, and then the balance of my career was in the oil and gas business. So I've got a pretty broad perspective on the space that we're going to talk about this afternoon. I'm going to share my presentation right now. Let's see if I can find that. Hold on. Upload file. Excuse me for 1 second here. Okay, we're back again. I thank all of you for your persistence. This is the last one of our panels this afternoon, but I think it's going to be a kind of an interesting one. And I already introduced myself. Here is the first slide of the presentation. So really, we're going to talk about critical mineral supply chains and talk about them in the context of potential bottlenecks. I'm very pleased to be joined by Dr. Thomas Benson, Dr. Tristan Childress, Dr. Parans Paranthaman, and Dr. Wen Song. And you can see their affiliations. They all have distinguished CVs, and you can read them in your program. Next slide, please. So I never give a presentation without advertising my program. And the reason I do this is because I really believe that this premise that we have for the Energy and Earth Resources graduate program is absolutely essential to solve any energy problem. And that is that to develop a sustainable energy solution, we must have viable technology. We must have a opportunity that attracts investors, so it's viable financially, and it must work at the interface with society. So it must adequately address the welfare of society. And that is exactly the premise on which our graduate program is based. We've been around for 40 years teaching students exactly that. Next slide, please. So here is the broad panorama. Here is the Venn diagram blown up a bit. And I'm going to start with economics and finance. And the way we're going to talk through this is we'll cover a number of topics: supply and demand, supply chains, and how they get us to useful products, because that's a really essential piece. We'll talk about government initiatives to address supply chain vulnerabilities on the policy side, and on the technology side, we're going to talk about increasing the efficiency of extraction. We're going to talk about unconventional sources of energy critical elements, and we're going to talk about mining sustainability. Next slide. Okay, what are these energy critical elements? Well, a lot of them are the rare earth elements. They're the lanthanide series shown in pink. People usually include scandium and yttrium, although those aren't lanthanides per se. All the other elements there are also elements that DOE has deemed energy critical. And the purple elements are ones that I have shaded because I call them energy vital. They would include, for example, the copper, the most probably essential of all energy elements. Next slide. Next slide, please. Well, how do we think about these energy critical elements? So many people will look at them in the context of these criticality matrices. And on this one, you see on the bottom supply, and on the top their needs for some of these higher technology applications that we talk about. In the upper right, we're talking about elements that are deemed energy critical and also relatively challenged in terms of our ability to access them as we need them. In other words, they're going to be the ones most prone to supply bottlenecks. So dysprosium, for example, elements that will be used in permanent magnets and wind turbines. While lithium is an element more down to the lower left where there's quite a bit of supply and we don't worry that very much. There's another way of looking at this. This is I'm going to call this the HH index. It essentially looks at geographic distribution. The further to the right, the more geographically constrained an element is. So and this shows this over time. It's kind of a very interesting representation. And what you see is, for example, if you look really hard, the rare earth elements have moved to the right with time as China has constrained this more and more, while lithium has actually moved to the left as more resources have developed. Light and heavy rare earth elements are consistently identified as relatively high risk. Next slide, please. Now, rare earth elements or energy critical elements, a lot of them have moderate to low abundance. They're not really rare. But numerous energy critical elements have high geographic concentration. For example, the platinum palladium series up on the upper left. And what you see generally is a correspondence, a linear relationship between crustal abundance and cost. The rarer they are, the more costly they are. Next slide. But we've just scratched the surface. Literally, this is the distribution of certain ore deposits, very important metals to the energy future. And you can see that over time, we've gotten deeper, certainly in terms of our mining of these metals, but we have a long, long way to go. Next slide. And we haven't touched the seafloor. The ocean represents 70% of the Earth's surface. And on the seafloor are, for example, cobalt nodules. There are rare earth crusts, rare earth element crusts. So huge potential resources that will have to be mined. And as they're mined, they'll have to be mined sustainably. Next slide. Now, the supply chain is comprised of mining these, which isn't usually the biggest issue, concentrating, refining, and manufacturing. And then the whole issue of recycling has become more and more important. I think it's going to be very important in the future. What I'm going to suggest here is it's this entire supply chain rather than the resource itself that really we have to worry about. The resources themselves aren't the biggest issue. Next slide. I've called this slide China REE Inc. There literally is now a China Rare Earth Element Inc. as China has consolidated number of its producers. Biggest single ore deposit in the world is the Bayanabo mine in China, and it actually produces rare earth elements as a byproduct. Most of these rare earth elements are light rare earth elements. There's secondary production from ion exchangeable clays in Jiangxing, and this is low grade but very cheap extraction, and they're heavy rare earth element enriched, so actually the more valuable in the rare element. The challenge in replicating what we see in China is not the resource itself, but this whole strategy that China has formulated. It's a national strategy: cheap labor, vertical integration, technology-specific intellectual capital, subsidies, and lax environmental regulations. Next slide. Well, this one, I guess I'm not really looking at the animation here. I assume you're going through a PDF rather than the PowerPoint itself. But if you were to look at it, what you see for rare earth elements is that once upon a time, not so long ago, 1990s, the US dominated rare earth element production. It's been completely surpassed by China. On the other hand, China isn't the biggest producer of lithium. Australia has been, but the lithium triangle in Chile, Argentina, and Bolivia are about to eclipse it. Nevertheless, when we look at lithium and we look at batteries, look where battery production is concentrated. So again, you don't have to control the resource to actually control the supply chain. Next slide. And the challenge in all of this is making mining sustainable. We dig big holes, we move a lot of earth, we produce a tremendous amount of waste in mining. 350 gigatons produced worldwide each year, which is 20 times all municipal solid waste combined. So this is our biggest waste form by far. But the question is this waste actually a resource in disguise? And we're going to be covering that a bit. All right, that's all I have to say. I'd like to introduce the next speakers. They're going to take no more than 5 minutes each. And the order in which they're going to go is Tristan Childress first, Tom Benson next, Wen Song next, and Paran Paranthamans, who's going to play cleanup here.
Hi, Richard.
Hey, how are you doing, Chris?
Well, pretty good. Let's see. Okay, I got my slides up, so I'll just go ahead and get started. Thanks for having me today on the panel. Some pretty good talks so far, and I'm happy to be here and talk a bit more about this with you guys. So I'm Tristan Childress. I work with the Bureau of Economic Geology here at the University of Texas. A lot of what we do here is applied research for oil, gas, water resources, and I, in particular, work on mineral deposits and anything mining related within the state of Texas. My background in particular is in volcanic geochemistry, so I have a lot of fun out in West Texas. So getting back to a previous slide that Richard just left off of, this 250 gigatons of waste every year that is created by mining. This infographic is really good to kind of get that point across. So here at the bottom we have the Burj Khalifa, and so this is the tallest building. I think it's still the tallest building in the world, and standing next to it is the Statue of Liberty. And so this giant cube represents the volume of iron ore that was mined in the year 2019. And so imagine this volume of ore being mined every year, and this cube gets larger and larger as we go forward and grow a bigger population. And so this doesn't even include the other metals that are being mined, but it's an enormous volume. And so we're going to need more and more of it as time goes on. And so that demand is primarily being driven by the energy transition from hydrocarbons and coal to wind, solar, and then battery storage. And then, of course, the Defense Department is a huge demand on these metals that we all need. And so in the International Energy Agency's recent publication in, I think, 2020, they ultimately came up with this somewhat round number that we will need to quadruple the amount of minerals that we mine every year to meet the 2-degree scenario by the year 2040. And if we want to transition even faster to hit net zero by 2050, we'll have to multiply that by about 6. So these are really, really large amounts of mining that we will need to do if we want to meet these goals. Recently, the United States, the Australian, and the Canadian geological surveys formed a partnership to help one another build really large national geospatial data sets. The point of this is to provide the public with the data needed to do efficient exploration of our natural resources. And so at the USGS, they have a program called the Earth Mineral Resources Initiative, which I'm involved in on the local level here in Texas. And this program is applicable to helping us better understand our mineral deposits, our groundwater resources, our energy sources, and as well as natural hazards. So it covers a wide range of uses. And so in the infrastructure bill that was recently passed at the end of last year, that added just a ton of money to programs like this to help the United States to better understand its critical mineral, what it has for critical minerals and where they're located and how they're being used. So we're really pushing to amp up our supply chains. So I'll skip a few through these. What we're doing here in Texas, we're looking out in West Texas where the volcanics are. We're looking closer at home, some materials that we have. We're looking at our lignite deposits to see if they have rare earth elements or other critical minerals that we can use. These are really big national scale projects that we're involved with. We're looking at our waste streams to see if we can take critical minerals out of those and make them useful again and clean up sites. And so you kind of get 2 in 1. And we're also taking a really hard look at the supply chains that are involved with creating windmills, solar panels, and batteries to really take a deep dive into the unique impacts that each of those will have region by region across the United States. And I'll leave it at that.
Tristan, thank you very much. And so Tom is up next.
Great, thank you. My name's Tom Benson. I'm the head geologist at Lithium Americas Corporation, which is one of the, not actively producing any lithium, but is on track to be one of the, if not the largest producers of lithium in the world by mid-decade. And so I'm grateful to be invited to this panel to talk about, the company perspective and definitely the lithium perspective on the aspect of critical minerals. My background is I started out doing geothermal energy research in undergrad and prior to grad school. But when I went to grad school, I did my PhD in volcanology and critical minerals. The question that I wanted to answer was, why does the McDermott caldera, which is on the Nevada-Oregon border, have so many different types of mineralization? It used to be the largest mercury producer in the world. It has rare earth enrichments, gallium enrichments. It has uranium, but the behemoth is lithium. In the Caldera Lake sediments of this 16-million-year-old supervolcano, it has more lithium than all of the salars in South America combined, according to recent research at the University of Nevada, Reno. And so that's the answer I set out to question my PhD. And now I always thought I'd do academia, but I'm find myself as head geologist at a mining company. And as a liberal environmentalist, it seems sort of antithetical to what I thought my career path would be. But I think it seems sort of natural once I, think about it, is because as we need to address all these solutions to climate change, as Tristan and Richard were mentioning, we need all these resources. In the solar wind farm approved off the offshore of Massachusetts, we need something the equivalent of, I think, 60 Statue of Liberty's worth of just rare earth elements alone. I forget the exact number, but somewhere, maybe it's like 30, but somewhere around there. But that's just in one wind farm. And so we need to find domestic resources. We also need to find resources that are sustainable. So in my role at Lithium Americas, I'm the resource guy. So I use my geological know-how and try to find additional resources. But from a company perspective, one thing you look for, we are for-profit business, but we want to find diversity in resource types, diversity in geography, and diversity in different types of ore itself, in addition to deposits, because you have a pegmatite deposit. Each pegmatite could have different types of lithium chemicals. It's a very complicated sort of supply chain. I guess I'll wrap it up by saying that, one of the reasons, Richard mentioned the importance of sustainability is one of the exciting parts of, starting the lithium demand is skyrocketing because of electric vehicles right now. And there's a lot of lithium out there. There's, more than enough lithium than we will need. But the issue right now is that we're already in a lithium shortage. The price of lithium has never been higher. And by 2025, it's going to probably significantly impact the price of electric cars, which may be a deterrent for, some consumers. So one of the things that we need to do, and we need to do quickly, is find lithium resources. Each mine takes, about 7 years to permit. So if we want to start in 2022, that lithium that's in the ground might not come out till the end of the decade. So we need to fast track permitting. We need all of government and industry and academia approach to help address this. And not only that, but the other exciting part of that is the sustainability aspect. Is as we're building these projects from scratch, we can build sustainability into the design. And that's one of the things that really excited me about my company is we're designing it from scratch right now. We just got our state permits all approved. It will be the first big lithium mine to come online in the US since the 60s. And will be a carbon neutral scope 1 mine, use less water than the equivalent of 2 alfalfa pivots. And because we're incorporating sustainability as well as input from the local community into the design of the project. And that's how, as we want to address the climate crisis, you have to be sustainable in how you extract, as sustainable as possible in how you extract that resource as well. So
great.
Thank you.
Tom, I think we'll have a lot to talk about when we talk about mining sustainability. Wen, you're up next.
Hi. So yeah, I'm Wen Song. I am an assistant professor in the Petroleum and Geosystems Engineering Department here at UT Austin. So I'm very happy to be here. And actually, Tom probably doesn't know this, but way back in grad school, I did attend one of your talks on the Caldera Lakes work. So it's great to kind of come back, and be on this panel with you as well. So I thought that I would just show a few slides because, we were asked to do this. So I think this is an idea that has already been discussed, by our panelists so far. But really, as we transition kind of from our current energy landscape, right, that's very carbon intensive, it's fossil fueled. And, as we migrate towards kind of more integration of renewable electricity, we're going to be using a lot of these mineral materials to actually make these devices function, right? So for example, in your wind turbines, you're going to be needing massive volumes of magnets. And so for example, neodymium is an important element there as we move into grid scale storage so that we can kind of offset the intermittency that we'll see with the renewable energy resources. Right, we're going to be needing massive volumes of things like, lithium and cobalt and other minerals. And similarly, when we kind of electrify our vehicle fleet, right, we're going to be needing energy storage and other minerals like lanthanides to actually make your car function. And so currently kind of the big bottleneck in terms of this transition has been in the availability of economic and stable material supply chain, right? So, if we, this has already been kind of hinted at a little bit, but, maybe more graphically, you can see kind of the production of rare earths, globally, right? So kind of over the last 30 or so years, production has predominantly been coming out of, a single country. And, these are environmentally deleterious processes. So, this is, again, the Bayan-Obo mine in Inner Mongolia, where they've effectively cleared the land, mined this giant open pit, right? And so, and then, to extract the ore, and then the downstream processing of that is also quite, heavy in terms of the reagents and the chemistry that we need to be disposing of later on. So environmentally, this is a challenge in terms of the market dominance by a single country, right? So if there were any kind of export controls on this material, as we saw in kind of the early 2010s, right, all of a sudden, for example, dysprosium, the price shot up tenfold overnight. So these types of supply chain disruptions have made it hard for us to really adopt some of these technologies on a broad basis because of the economics. And so what my group, tries to work on is to look at alternative resources for these critical minerals. So here, we've come up with a few maps of, resource types across the U.S. And so you'll see that, there are significant resources actually within the U.S., both in, produced waters and things like coal and coal wastes. So this is quite exciting. And a big part of my research program is to actually turn, some of these waste materials that would otherwise, cause environmental hazards like acid mine drainage, and instead extract them and turn them into something useful like neodymium magnets or other materials. And then just a quick example of some of the things that my group does is in terms of kind of the micro and nanoscopic characterization of the material itself, but then also of the extractive processes and the separation processes. And so here we leverage a lot of micro and nano visualization techniques. So we develop and use them to try to understand these kind of multi-phase reactive transport phenomena that are occurring within these granular and porous materials. So I'll leave it there and happy to discuss.
All right, great. Parans, you are the cleanup hitter here before we have our moderated discussion.
Okay, thank you. Thanks for the opportunity to talk about lithium here. And I am part of the Critical Materials Institute. So it started like 9 years ago. So I'm working on recovery of lithium from brines and minerals. And also I'm working on additive manufacturing of rare earth magnets, specifically, which has 100% yield. You can recycle and remanufacture as part of this project. And this was funded by US Department of Energy and EREAMO office, and I am a corporate fellow at Oak Ridge. And I was a postdoc working with Professor Goodenough, like a long time ago at UT Austin. So it's bringing back memories. And I have a funded project working with Ben Song right now on the recovery of lithium. So let's talk about, we already saw Tom and Richard touched on, and also Ben, like lithium forecast, if you look at the top left. So even though the battery is the predominant thing, lithium is also needed for several other applications. So it's going to go up in the next future. And if you look at the production on the top right, even though it's all available right now, like mostly Australia, China, Argentina, Chile, that's where all the lithium is made. And including North America, right now, Canada and US, we have just 2% production. We do really need domestic supply chain. We don't have it yet. And if you look at the Rascal report of lithium carbonate cost, people can report like, okay, the cost can change $4,000 to $8,000 per kilo for per ton for lithium carbonate equivalent or lithium hydroxide. Some report brine is cheaper versus mining, so it depends on this, but it doesn't matter. But if you look at the cost right now, it's increasing. We are already in the $40,000 per ton, and it's going to go up. So I agree with Tom. We really need a domestic supply chain for the forecast, what we are going to do with respect to electric car and other clean energy applications. So if you look at the types of resources, minerals, so you can see like 145 mineralogical species. Spodumene is the main mineral we talk about. So we do work with some like sedimentary clays in boron, California, Rio Tinto boron or iodorite. Seawater is, even though low, that's also can be interesting. And if you look at all this, recycling is another opportunity possible. And if you look at the like brines, and as we talked about, like Richard touched on, so the initial, like mainly ABC, Argentina, Bolivia, Chile, that's where the lithium concentrations are very high. But however, the recovery of lithium can take 18 months. And we have been working on salt and sea for geothermal brines. We started working with symbol material, and we have developed a lot of technologies, and they are not there anymore. And if you look at the top left, this sand fault region, that's where the lithium came and dropped in this sea, the salt and sea area. So we have enough material, but we do need cost-effective processes if you want to look at brines, and we have opportunity for produce water as well. So what we did was we developed like lithium double hydroxide chloride based sorbents, which can recover like more than 90% of lithium chloride from the brines. and it's very cost effective because you don't need to add any chemicals. We use the chlorine affinity, and then we develop forward osmosis. So once you have 3% lithium chloride, you can concentrate to 20% chloride. Then one can convert to like lithium carbonate or hydroxide. So we work with Purdue University on the life cycle analysis, and the lithium carbonate produced from the geothermal brines have like 34% lower carbon footprint compared to salt flats, or even 26% uh, less production with respect to mineral spodumene. So all these opportunities are there, and we are looking at other sources right now. And also we have done like techno-economic analysis. So we have opportunity to combine these sorbents and the forward osmosis. It will have like economically feasible, and capex opex is payback time is only 1 year. So there are opportunity. If you were to take 50 megawatt geothermal power plant, one can produce almost 16,000 tons per annum, so which is a big deal. So if we have, there are about 20 power plants in that area. If we can couple similar technology, and we could produce the world production of lithium right here in the United States, and we could be not just the importer, we could be the exporter. And I'm not talking about mineral, but I'll be happy to talk about other opportunities what we have. And thank you.
All right. Thank you, Parans. That's great. I broke kind of the discussion down into a number of parts. We may wander from one area to another. I'm going to guess we will, but I'm a geoscientist, so my natural inclination is to kind of start with the supply, maybe the supply and demand side. And I know obviously Tristan is looking broadly from an academic perspective more. Tom is looking at it from a commercial perspective. So, I think everyone said scarcity may really not be the issue, but we have to find the stuff, and that's not something we've done enough of here. I will maybe throw out a question, which I always ask, which is why do we really need to try to duplicate something that somebody else, in this case, say for rare earth elements, the Chinese have done exceedingly well? We know it's going to come at a very high cost. So I challenge any of you all to address this question. Tristan.
I mean, I'll jump in. I mean, the simple answer is just security. If we allow someone else to maintain our supply lines, and that someone else one day decides that they don't want to give us that anymore, we'll be in a really bad spot.
Right.
And really, that's what it boils down to, in my opinion.
But would you agree that it's not just that? I mean, if they don't want to give us the supply anymore, and we can find the stuff and produce it ourselves, if they still manufacture the batteries or the permanent magnets, don't they have almost as much control as they did before? I mean, Mountain Pass rare earth elements are going to China for processing. So, this is a question, I guess, at the end of the day, at what cost? Yeah. And I think that's what everyone is mulling right now.
There are, we have to identify the bottlenecks, and, there's bottleneck after bottleneck. And so fixing this one, you still have to fix this one, because there's still this bottleneck of manufacturing that we don't do.
Yeah.
And, do we need to do it all? Probably not, but it's good to have that capability in the worst case scenario.
Yep. Tom, you're looking at this and trying to make money doing it. At the end of the day, how are your costs going to compare with, say, lithium produced from the salars in Chile?
Yeah, I mean, there's a lot of factors, as you pointed to, when talking about the supply chain. The geographic diversity is important for the reason Tristan mentioned. Just could you imagine a situation where Russia controlled the world's lithium as we're trying to electrify all of our fleet, and now Russia invades another country? It's not a hypothetical, and guess what? Where do we get our lithium? We can't electrify our vehicles. So from a geopolitical standpoint, it's really important. From a cost perspective, I know when prices right now, as Farhan's pointed to, are like $40,000 a ton. A brine costs about, say, $3,000 a ton to process. Spodumene, say, $7,000 a ton to process. So from a company standpoint, when the price is this high, it doesn't matter. You're still making a profit.
So
But then,
if you're willing to divulge, where do you all sit in terms of cost to produce and process?
yeah, so that we have a couple different assets. Our brine project is typical of most brine operations, around $3,000 a ton. Our 2019 pre-feasibility study at Thacker Pass, which is the only number I can legally reference, was about $4,000, $4,500 a ton before credits.
So it, competitive.
Yeah, so it's better than spodumene deposits. And so that from a cost perspective, that doesn't really matter. But then you have to, we as a company are trying to diversify our resource types and locations, as I mentioned before. So that's also important. And the other thing that's important, as you mentioned, was the whole supply chain, the manufacturing. Right now, our Nevada project is, the largest Salar de Uyuni, Bolivia, has I think an estimated, I forget the exact number, 40 million tons of LCE. The McDermott caldera has 120 million tons of 640 million tons of LCE. So it's like an order of magnitude bigger. And so we have the resource in the US. It's sitting right in Nevada. We have Tesla, which is right there in Reno as well, just hypothetically. But right now, as you mentioned, if we wanted to sell our lithium to Tesla, you have to make the cathode before you make the battery. So we would have to send the lithium from Thacker Pass to Korea, Japan, or China to make the cathode. And that lithium has to go all the way back to Nevada to the gigafactory in Reno. So that cost is huge. That carbon footprint is huge. And so the supply chain is not vertically integrated. So there are companies like Redwood and some other companies that are developing cathode manufacturing within the United States. So that, as you mentioned, has to play a critical part of this drive towards domestication.
We in the discussion, I think both Wen and Paran's brought this up, obviously, and so did Tristan, that there are all of these, let's call them unconventional sources of lithium and rare earth elements that we might be able to exploit. And I'd just like to kind of address that one, both from a viability, technological viability, and a cost perspective. Maybe Wen can take a crack at the coal ash story, or coal-related rare earth elements, or any of the others that you're working on.
Sure, yeah. So in my group, we are currently working on recovering or assessing rare earths from coal and coal waste materials. So, for example, fly ash, and as Parents mentioned, we have a project together on recovering lithium metal directly from produced waters in the United States. So, I suppose in terms of the feasibility, the technological feasibility. I think it's a major motivation for us is how do we actually do this in an environmentally, benign manner, right? Yeah. Because a major reason why I think in that plot that I showed of rare earth production globally, kind of in the 80s, 70s, that was really dominated by the U.S. The reason why it kind of tailed off towards the 2000s is because of all the environmental regulations, right? That these processes could no longer meet. And the economic kind of, driver for that was just, it was not possible to do this in the US anymore. And so a big kind of part of the challenge is, we know that there's a lot of this stuff around. So, for example, in the coal fly ash, we're identifying upwards of 1,000 or 1,500 ppm of rare earths, right? So it's relatively elevated, and there's a whole lot of it If you do the math, actually, the amount of, even today, as we are kind of ramping down on coal combustion, even the amount of fly ash that we're creating now, if we're able to extract all of the rare earths out of it, that would almost supply the global demand annually. And so there's a lot available. The question is, how do we do it in a way that is cost efficient and environmentally benign?
Yeah, the coal fly ash one makes sense to me because it's sitting out there, and actually, obviously, a huge environmental nuisance. I was kind of amused. Tristan will probably remember there was some presentations on looking at the rare earth elements from the immediate hanging wall of some of these coal seams. I think in the Illinois Basin. I don't remember exactly where, and I thought to myself, well, surely you're not talking about mining coal to produce rare earth elements. It seems a little counterproductive. And being a miner myself, mining that little bit of rare earth element is going to be very costly. So really, my question is, at the end of the day, as an old miner, it's looking at a correlation typically between grade and cost of production. And the less concentrated something is, the more it typically costs to produce, all included. So what you're saying is, in the case of rare earth elements, you've actually got concentrations that are competitive.
Yeah, that's right. So then it's a matter of how are they actually distributed within these, tiny little glass spherules, right? And so, and how do we actually access those rare earth bearing, mineral grains that are, maybe on the order of about a micron or so.
Yep.
But how do we actually, extract that and kind of in a way that, we're not using massive volumes of leachates or reagents or something like that.
Nasty things. Parans, you mentioned lithium. You mentioned lithium from petroleum brines as a possibility, and I actually happen to have done some work with a student on the very topic. So I'm interested in where you all are going with this. One question again is, typical concentrations are very low. There's some in brines like the Smackover brines, which are significantly enriched, but they're I don't think people fully understand the distribution. I'm going to call it of grade, but let's call it of concentration. So address that question. I mean, you talk about extracting, let's say 200 parts per million, a 200 part per million brine versus a 800 part per million salar brine. How do you possibly compete?
I think the one thing I talked about technology, what they do in salar brines is it's taking solar evaporation 18 months, whereas the process we have developed is instant. So you are going to separate it continuously. So you can do like within a couple of days. So that's where we are coming into play. And the other thing is these are aluminum hydroxide chemistry, cheapest material, earth abundant material. And when we develop one chemistry on, for example, geothermal brine, so we learn the whole science about it, what's going on with respect to the separation and concentration and conversion. And we can use the same technology for mineral, because that's what we see a different stream like chloride stream. So we work with Rio Tinto on the sulfate stream. So they don't have to mine it because they are already producing the boron compounds. So these are tailings has really like almost 2000 ppm. So what we learned from the brine chemistry, part of it is already used for the mineral. So that's how I am thinking, like maybe what you learn from one area and we can go to produce water or any of the other areas. And the key thing I always talk about, when we focus on lithium, you cannot be business-wise economically viable. So you always want to look for some byproducts. That's where the potassium or other manganese or zinc, same thing, Tom, when he's going to look for lithium, he's going to look for other byproduct that can improve the value-added product. So these are the opportunities we have.
So to play devil's advocate, could we take your technology, a technology that allows recovery at much lower concentrations in a more rapid time frame, and apply it to the salar brines? So you don't have this issue of massive areas of evaporation ponds that need to sit there for 18 months to produce the lithium carbonate.
And the technology we developed is kind of temperature specific. So it may not work at ambient temperature. So we may have to engineer the solvents. So currently the ones we developed, it may operate from 60 to 90 degrees Celsius. So what we need is, if we were to use the solar brines, we may have to warm it up or heat it to use the solar heat or CSP to heat it up to 60. Then the technology we have developed can be used. So that's for now. Otherwise, we have to modify it to the thing. That's why we are looking for other methods, like the one Ben is looking at, maybe electrodialysis method or electroplating, other processes for ambient temperature. So that's what we're looking at right now.
If I could add on to that, I think it's an important point. The technologies that you're working on and others are working on, especially in the direct lithium extraction space, are really important and will play, hopefully, an important role in adding to the supply of lithium that we have. But if you look at some of the projects, for example, that are actively trying some types of direct lithium extraction, say in the Salar de Hombre Muerto in Catamarca, Argentina, they require a lot more water than the traditional solar evaporation ponds. And water is one of the prime issues to the local community up there at 4,000 to 5,000 meters of elevation. So the price of it and the environmental footprint, the environmental footprint isn't just the ponds, and it's also a function of time, it's the amount of water, and the other aspect of that is the waste. When you do direct lithium extraction, what do you do with the wastewater as well? So each project has to have a different, unique process, and that's why doing this research is so important. Like each clay project, for example, has a very distinct process for extraction with variable degrees of water consumption and energy consumption. So they all need to be optimized in order to reduce the footprint and cost.
Yeah, I was going to go to the water topic, but you've addressed it. I grew up in the Atacama Desert, was born and raised there, right next to one of those big salars. So when I look at even brines and evaporation of that as a reduction of the hydrological resource in the Atacama Desert, that's worrisome. That's something that it would cause people, I think, to think hard about that. Tristan, you're working with USGS on resource distribution, identifying new resource opportunities. We have one, I guess, in our backyard at Round Mountain.
Round Top.
Pardon me?
Round Top.
Round Top. I always confuse the two. Round Mountain is a gold mine in Nevada. Yeah, Round Top. Yeah, can you talk about that? Where obviously rare earth element deposit, but what's the prospect of its development? What difference could it make as a supplier of resources?
Sure. So Round Top is in Sierra Blanca, Texas, which is about an 8-hour drive west of here on I-10. And it's really way out there, but it is a part of a rhyolitic complex. So there's a few of them out there, and it probably isn't the only one that is potentially economic. Round Top originally was a beryllium prospect, but it has since become a all-in-one go-to. So one of the things that makes Round Top special is that it is elevated in the heavy rare earth elements, which is somewhat unusual. And so that is one of the things that make it very economic. They're kind of attacking it from a holistic standpoint, that they want to get the heavies, the lights, they want to get the lithium, they want to get the battery metals, they want to get the aggregate. So they want to kind of pick it apart and put it in its little bins and sell it all off. And they have a model for that. And, it's on the order of profit is on the order of, $1 billion or so, total. And, so, I don't remember the exact tonnage, but it's quite a bit. And if it opens and it becomes active, it will be the largest. It will be larger than Mountain Pass. It will be producing more than Mountain Pass in California. And it will be one of the largest heavy producers in the world, if not the heaviest.
What are the biggest obstacles right now to its opening?
I don't know. I think they're very close. It's one of those situations where, just 2 more years. But they've been going for a long time, and I think they're very close to opening now. And they've been working with the Department of they've gotten funds from the Department of Defense to develop new types of ion exchange, or to, I guess, tailor the ion exchange process to their deposit. So I look forward to seeing where they go. I think it can absolutely become a viable deposit, and I hope it does soon.
I'm gonna throw one last question before we go to maybe questions from the floor, and that's to all the technologists. That includes basically all of you, and that is the issue of technology obsolescence. So, Parans, you worked with John Goodenough, and you mentioned obviously lithium, and we have a co-inventor of the lithium-ion battery, but he and Maria Braga are working on maybe a glass that doesn't require lithium at all, that could be a very viable battery. I'm bracing that as an example of something that could instantaneously disrupt potentially a market like that. What are your perspectives, or what are your perspectives on that very topic?
So if you look at the lithium ion chemistry, so Professor Goodenough developed in 80s, then 90s. So it took almost 20 to 25 years to mature the technology, and we have come so far. So, but if you look at alternate, we are also looking at sodium ion battery, potassium ion battery, or even solid state batteries or other batteries. But my feeling is still it's in the research stage. So any technology that's developed today, it's going to take another 10 to 15 years from now.
Yeah.
And the challenge is always the lithium ion conductivity. And even though there may be more claims about very high conductivity, we always feel like maybe if there are other ions contributing in addition to lithium, maybe proton or something else is contributing. So we still need to clarify it. And I am aware of this new technology. So we need confirmation. And the same thing, direct lithium extraction, I feel like so many companies, labs are saying like they have developed it, but nobody has seen the data. So
Right.
we really need like an international somewhere standard, either in a national lab or a university, where companies and others, they can come and test it or so. So that's where we are proposing a concept where we can go from the extraction all the way to manufacturing. Tom talked about separation, conversion, batteries, large scale. So where we can create this as a national lab infrastructure, where the companies can come and test it. So,
well, I'm going to take questions from the floor, and I think David Tuttle is the Wizard of Oz sending these questions out. They flashed up on the screen so quickly, there's no way I could read them. So David, if you could put some of them out so that we could see them. I know one of them was a question. I will start with that one. Well, here it is. At what number of U.S. electric vehicles on the road will the new supply satiate the demand, and is recycling a real important part of that equation?
Yeah. I think recycling and remanufacturing, yes. Definitely,
yes,
that's
are going to be very important.
Really very important. And we have not been doing much at all. So I think that's going to be, that's where the infrastructure bill, we do have the recycling and remanufacturing.
I mean, is part of that, I mean, I just kind of, Tristan having a background in maybe mining as well, is part of that the fact that you can probably find more and more of this stuff, but it's going to get to be at a higher and higher and higher cost as you go deeper, or you go hotter, or you do whatever you have to do. And so that cost is going to move to the cost of an electric vehicle, at which point you're going to say, gee, this vehicle is way, way too expensive.
Yeah, and Tom knows this as well, is that, just from an exploration perspective, the quality of ore deposits that we find is going down, and it will continue to go down until we go to a new planet and go there. So it's going down, and so imagine you have a 2% copper deposit. That means 98% of your copper deposit is waste rock.
Yep.
And then imagine you have to go to a lower grade, so 0.5% copper deposit. Now you have gone up, just a crazy amount, 4 times the amount of waste. And so, it's recycling has to happen. I mean, it has to happen.
Yeah, Chile copper, 1990, about 1.2% average grade. Now it's 0.45% average grade. That's the biggest copper producer in the world. So yeah, right where all the lithium deposits are, by the way, just a little outboard of those lithium deposits, which also demands water. Okay, next question. All right, what is the biggest deterrent for geothermal lithium extraction to take off from technology, economics, regulatory perspectives?
Yeah, so the ones I wrote was mainly like we are not extracting lithium from the power plants. So we are just extracting from the waste that's coming out from the power plant, because otherwise it's going to be injected back into the ground. So I don't see maybe the regulatory issue. So that's where I think my feeling is, either with respect to geothermal or mineral. Like Rio Tinto, they are already mining. So if you don't have to drill or mine anything, that's a best case scenario for us.
Yeah.
If you are to go, and Tom said he has already all the asset owner, maybe he has everything, so then you don't need to worry. But if you're going to drill something or extract, that's where the issue will come. So
yeah, I mean,
don't
this is where what Wen is working on, say coal fly ash. I mean, that's something that has been mined. That is something that is an environmental nuisance. Can you, in a way that's not more environmentally damaging, can you extract something from that to make a useful product?
Yes.
Yeah, and maybe I'll just add on to that. So if you think about kind of the fly ash perspective, we have all of these acid mine drainage, problems around the US, right? And that's really a result of, basically rainwater coming in through these heaps of the fly ash particles and basically leaching out some of these heavy elements that are, poisoning our waterways. And so these materials are not, a lot of them are bound relatively loosely in the sense that, we don't need a whole lot of reagents potentially to extract all of them. And so there's an opportunity there. And then in terms of, I think, the geothermal brines, so if you look at kind of the concentrations of, for example, lithium in the geothermal brines, right, those are on the order of about 10 ppm, whereas, in other materials like produced waters from oil and gas wells, they can be anywhere up to, say, 1,000 ppm. And so the very, very low concentration is something that has been challenging. And then the presence of, other dominant cations like, sodium and potassium and magnesium and calcium, right? These are things that are competing for separation. And so that's a main reason for kind of why geothermal brines are still a little bit far out.
Yep. I think we have time for one more question. Well, this is going to be touching a little bit, Gwen, on where you were. Is there enough coal fly ash available? It does a lot of good for concrete, lowers porosity, heat of hydration. So, is there going to be competition with other demands potentially for coal fly ash?
Well, I suppose you could think of it this way. So in the some of the pictures that I showed, right, we are looking at fly ash particles, but we're not actually trying to dissolve the entire particle. We're just trying to extract, leach off the things that are useful to us, right? And the remaining material are the silicates and the aluminosilicates that, can probably still be a pretty good concrete material. So it might just be an value add to the supply chain.
Yeah. Okay. Very good. Well, I actually had about 20 more questions, but we're not going to get to them. So Wen and Parans and Tom and Tristan, thank you all very much. That was an interesting discussion. I learned a lot. And I guess as the last panel of the day, we'll say thanks to our remaining audience. And we'll look forward to continuing the discussion in some way.
Thank you. Good to see you.
Thank you very much, Richard.
Bye-bye.